I said that in vectors there are a whole heap of different topics that we need to be able to cover, and hopefully we're comfortable now with those, quote unquote basics, right? So it's like, just adding them or subtracting them, writing the notation. What else did we look at yesterday? We looked at kind of the more complex operations, right? So we looked at magnitude and direction, and we looked at how that's essentially just, Pythagoras' theorem and also using tan, right? So that's the idea with our vectors in terms of the basic operations that we can do. Now we're sort of moving on to ones that are a bit more complex. And Harry was kind of talking about how, hey, if there's a form, you just put it in and then boom, you get your answer. And that's good because that applies to a fair amount of these types of questions. But obviously in the HSC, they have the freedom to kind of ask you these more complex and varied type problems, right? And so what I want to talk today is about the projections formula, right? Because the projections one gave people a bit of trouble. I'll write out the formula first, and then I'll let you decide the best way you want to approach this one. So here's the formula. The projection, and the order of the projection is very important, and I'll show you visually why in a moment, right? The projection of, and this is read as P onto Q, and the way you remember that is, well, P is kind of above the Q in this case, right? Now, there's going to be a fraction involved, but the important thing to remember about the projection is that it gives you another vector. So keep that in the back of your mind that you want to get another vector when you get this, right? So here's the formula for the projection of P onto Q. We take the dot product of the two vectors that we have, right? On the denominator we put the magnitude of Q all squared. Sorry, that's meant to be Q. So I did write it down, right? Is that what I wrote down on your papers? Yep. Did I write that down? Okay, cool. And yeah, this is why, this one, is that on your formula sheet? Can you check over there? Is it over there? Yeah, okay. This is why not a big fan of formulas because they're quite easy to muddle up and forget, especially when in your textbook they use U's and V's, and U's and V's look very visually similar to each other. So that's why I use P's and Q's or A's and B's to memorize that. I guess one way you want to memorize this, if you need a trick, is that, so it doesn't matter which way the projection is written, but you always have the dot product of P and Q on top, right? But remember I said the order of the projection is important. So if we change this, so I made the projection of Q onto P now, right? Then although the numerator stays the same, then on the denominator now, and over this part, you have what's on the bottom here. So the differentiating factor is what's it being projected onto, right? So that's P absolute value squared, and then P over there, okay? So that, just kind of be aware of that there, right? All right. Now, one kind of thing that you may be wondering is, don't these Q's and things sort of like just cancel out over here, right? Well, the issue is that when we multiply vectors, remember, it's not the same as when we multiply numbers, right? Harry, what did we call this guy again? What kind of multiplication was that? Dot product. And the way the dot product works is, what is this going to give you? It's actually going to give you a number, right? Whereas this guy over here, this is a vector. Yeah, can you see that? And if we take the magnitude, remember when you took the magnitude, what did you get at the end of that as well? When you did the magnitude of a vector, what are you actually finding? You're finding a number which represents its like length, right? So can you see how this part is like a length? So that's the length, that's the dot product, and then that's a vector. So essentially what you're doing is, whole thing is going to be a number, it's just a fraction. This itself is going to be a vector as well. And I guess the reason why it's easy to confuse, it's just with practice. And obviously I need to do a bit more practice as well with this one here because it's new content, right? And so I need to encourage you guys to be very familiar with this formula here. You just have to do it. It's just going to be like quadratic formula. You've got to do it enough times so you don't forget about how to actually approach this question, okay? Let's look at the one in your example. What question was that one there? What were the values in your one, Kyle? Can you give them to me? In question 11C. Just have that open for me.
P is 4 and then minus 3.
Minus 3, cool. And Q?
Minus 1 and 2.
Minus 1 and 2. Harry, I might have gotten it wrong in my answers, so don't copy those ones. Okay, so projection of P onto Q. No, because I think I did the wrong formula.
I think you did.
Yeah, okay, so ignore my answers there. All right, so projection of P onto Q. Right, I've got my dot product of P and Q. And then I've got the magnitude of Q, all squared, multiplied by Q. What I actually do is I tend to write this out in the separate components that I have, right? So I'm going to get my P and Q dot product first. And remember, that's multiplying the x coordinates together and then adding that with the y coordinates multiplied together, right? So 4 times negative 1 plus minus 3 times 2. Okay. James, do you want to calculate that for me?
Harry's got that quick now.
He does. Sorry, Harry, you stuck in there, negative 10. James, you have to do the next one for me.
It wasn't.
Magnitude of Q squared. You might want to start with just the magnitude of Q, right? What is the magnitude of Q? Remember, it's always just related to what theorem? Pythagoras. So you take Q, you apply Pythagoras' theorem there, negative 1 all squared plus 2 squared. But if I'm finding the magnitude of Q all squared, what can I just do with this guy? Yeah, right, exactly right. So it's actually going to be quite a nice number. Yeah, that's a nice number that we like to see. All right, so 5 there. We've got all these components together. All right, so you're ready, yeah, you're jumping ahead, good. So the projection of P onto Q now, you can substitute it into this. So I've got my dot product, negative 10 over magnitude of Q all squared, so that's 5, outside of my Q vector, so negative 1, 2, and that's going to be negative 2 outside of this, and 2, negative 4, looks like. Is that what we got? Yeah, all good? Yeah?
You did it a weird way, so but it worked.
Okay. Classic. All right, cool. Any questions about how that actually works? You can see it's a simple case of substitution, right? See how it changes now when we do another projection. Let's do the projection of Q onto P. I'll do it up here. Can you do that for me? Yourselves. So again, the formula is the same in the sense that we have the dot product on top, but now this one in the denominator, we've got the magnitude of P all squared, and the vector we're multiplying by is P. Okay, can you have a go at that one for me? Cool. All right, Eva, you can redeem yourself now then. What did you do for this one, which you've already done?
Well, Q times P is
Yeah. And we already have that over there, hey? Yeah, so that's fine. So the dot product still stays the same. I know in some textbooks they like write that order differently, like they swap them around because just to make you remember that it's a bit different, but nothing too important. The dot product doesn't matter what order it's done for these two vectors. Yeah, keep going for me.
and then I got P squared of magnitude of P
Yeah,
squared is
yeah.
25.
Cool. So we do Pythagoras' theorem here. We get the square root of 25, but then we're squaring it. So that just becomes, was it 5? No, 25.
5 and then P squared.
Yes, 25, sorry, yeah. Cool.
And then just put it with the vector.
Good.
for P.
Yeah, perfect. And this guy simplify out, negative 2 on 5, look like.
I got negative 8 on 5.
Yep, and either way, you can leave it with the scalar at the front, or you can multiply it back in. So you got what, negative 8 on 5 over positive 6 on 5? Yep, cool. And there's your projection of Q onto P. So again, just to emphasize, they may give you this notation, or they just may say it in words, but just remember that's onto P, and this one's onto Q, right? So those are the two differences between them. Okay.